All right, so it was suggested that I tell you guys a little bit about who I am before I start my talk. For those of you that haven't met me before, I am an astronomer masquerading as a planetary scientist. So my background is in astronomy, but I study planets like all of you here. So I find myself these days surrounded by geologists and people who know a lot more about planets than I do. So I've learned a lot from them. The topic of my talk today in the program is a little bit different than the topic on my slide. You might notice that the program said I would tell you about characterization of transiting planets. So when I sat down to start writing my talk, I realized that there was no way I could possibly cover all of the different things we can do to characterize transiting planets in 25 minutes, give or take. So I decided to narrow it down a little bit and focus in on atmospheres. There's lots of interesting characterization to be done on the dynamics end as well, and I think people have touched on that a little bit earlier in the week, but certainly for anyone who would like to chat about the dynamics side, I would be happy to talk more about that later. So, focusing on planets for now, I think that being in a planetary science department, I can tell you that there are some big differences between those of us that study exoplanet atmospheres and those that study solar system planets. And the main difference comes from the amount of information that we have on each of those bodies. So for the solar system, we have spacecraft that have done flybys, we have beautiful spectra, we have maps, and for exoplanets, often the information that we have is much more limited. So our ability to make definitive conclusions for individual planets is often, it's very rare to know exactly what the atmospheric composition of a given exoplanet is. So more commonly, what we do for exoplanets is try and take sparse information on individual planets, collect a really big sample of planets, and look for patterns in what we see. So what I'm going to tell you about today isn't necessarily unique observations of exoplanet atmospheres, but rather using some simple constraints to search for trends in the population of planets that we see that are going to kind of fold into the trends that you've already seen earlier in, for instance, the mass period distribution of exoplanets. So we're adding another dimension to those plots that's going to tell us more about how these planetary systems formed and evolved. Okay, so this I think is a good starting point for a discussion on characterizing extrasolar planets. So this is if you take the results from all of these large surveys that are going on and take only the subset of planets for which we have measured masses and radii. So most of the planets on this plot, their radii come from transit observations, actually all the radii do, but their masses are coming mostly from radial velocity measurements. There are a few things on this plot with masses from transit timing variations. So if you have a multi-planet system, the planets perturb each other, and from studying the mutual perturbations, you can constrain their masses. But most of the planets on this plot have masses from radial velocities. So there are on the order of 200 or so planets on this plot. That number is much smaller than the number of planets that have been detected by the various surveys. So you can already tell that by putting these two things together, we're narrowing down the population of planets that are available to study. So if you plot mass versus radius for all of these planets, you can see that there's a general trend where planets which are comparable in size to Jupiter and Saturn, these red stars here, have radii which are large enough that they must have a significant fraction of their mass in the form of hydrogen and helium. And that as you move down to smaller planets, here are Uranus and Neptune, that they have somewhat higher densities, suggesting they have larger rock or ice cores. And that as you get all the way down to the lowest mass planets, there are a subset of planets which appear to be primarily rocky in composition. So there seems to be a pattern that's emerging from these very simple measurements, but there are some limitations to what we can tell from mass and radius alone. So one question that we might ask is whether or not this trend is really telling us about how much hydrogen and helium a planet retains. So are these planets small because they're all water, all rock, or some combination of the two? Or can some of these planets still have significant hydrogen atmospheres? So how does the atmospheric composition vary as a function of planet mass? So this is adding sort of another layer of complexity onto our picture of these planets. But at the same time, if we can get that information, it's going to tell us a lot about how they form. Planets that accrete little planets, which manage to hold on to a lot of hydrogen and helium, might have very different histories than planets which are made primarily of water with a little bit of rock. So if we could tell the difference between those planets, we might learn something about where they came from. Another thing that we'd like to know is most of the planets on this plot have very short orbital periods. So this distribution may not be reflective of exoplanets as a whole, particularly at the low mass end. This is almost certainly also sculpted by mass loss processes. So to what degree is this drop-off telling us just that close-in planets don't have very volatile, rich atmospheres, versus how much is this a fundamental property of planet formation? So being able to measure atmospheric compositions will also let us address this question of the relative role of mass loss in these processes. And so I think maybe the most interesting region on this plot is the one here on the left. So you guys probably have already had lots of discussion about this class of planets, which we call super-Earths. We have no idea what they're made of. For convenience, I'll define this as planets with masses between 1 and 10 times the mass of the Earth. So this is where a lot of interesting things are happening. So this is where the density is dropping off significantly. At the same time, you can see that at a given mass, there's a very large scatter in radii. So there seems to be a lot of diversity in this population, and we don't really understand where that diversity is coming from. So another reason we might be interested in studying super-Earths is this sort of very lively and ongoing debate about where these super-Earths come from. So we see many super-Earths very close into their star, and there are sort of two schools of thought, one being that these planets probably formed farther out in the disk and then migrated inward. So that would be, if you think that sort of a minimum mass solar nebula, if you think there's not a lot of mass in the inner disk, the only way to get that many big planets close in is to make them farther out and then migrate them in. At the same time, there are a number of papers that have come out that said it may be possible to form these planets in situ. So if you do that, you would expect to see very different compositions than if you have something that formed farther out and migrated in. So if we could measure the water content of small planets, we might be able to constrain their formation locations. So this is a nice idea in theory, but in practice, it's a little bit more complicated. And I can illustrate that by showing you mass versus radius, sort of zooming in on the region around super-Earths. So you might notice that a number of the super-Earths here seem to have masses and radii that are consistent with primarily water compositions. So you might look at those relatively low-density super-Earths and say, aha, these things formed far out in the disk and then migrated in. We know they can't just be balls of rock. But the problem is that, as I mentioned before, we think some of these planets might still retain hydrogen-rich atmospheres. So if we took a ball of rock and added hydrogen and helium onto it, we wouldn't have to add very much in order to get something with exactly the same mass and radius as a water-dominated planet. So in this sort of intermediate density regime, we can't tell the difference between a ball of rock with a gas atmosphere and a water-rich ice world that migrated in from further out in the disk. So as you might have guessed from the start of my talk, the key to distinguishing between these two models lies in being able to measure the atmospheric compositions of these super-Earths. So if it's a ball of rock with a lot of hydrogen and helium on top, we should be able to detect the signature of that hydrogen-rich atmosphere. At the same time, if it's this scenario on the left, we would expect to see a relatively hydrogen-poor, water-rich atmosphere. So if we can measure the atmospheric composition, we can break this degeneracy in the bulk compositions of these planets. Maybe not completely break, but certainly get a lot farther along the path of figuring out what's in the interiors of these planets. Okay, so if we want to study the atmospheres of exoplanets, there are sort of three main techniques that are commonly used. And again, there are other techniques which have been used recently to study exoplanets, which I'm not going to touch on today. I picked these three because these are the most commonly used techniques, and I still think probably some of the most informative in terms of the quality of the data that we're getting out. So the first technique that I'll tell you about today is transmission spectroscopy. So when the planet passes in front of the star, if the planet has an atmosphere, that atmosphere will be opaque at some wavelengths and transparent at others. So if you measure the amount of light blocked by the planet when it occults the star, the wavelength dependence of that transit depth will tell you about the absorption from the planet's atmosphere. So this is a way to determine atmospheric compositions for exoplanets. If you wait approximately half an orbit, that same planet is going to go around behind the star and disappear and reappear. And so we refer to that as a secondary eclipse. So typically, secondary eclipses are observed at infrared light. And the reason for that is that we're trying to detect thermal emission from the planet. So if you do this at multiple wavelengths, the thermal emission spectrum tells you both about the temperature of the planet, how it varies with height in the atmosphere, And it also tells you about the composition of the planet's atmosphere. And again, you're actually studying different parts of the planet's atmosphere. So here, you're seeing starlight transmitted through the day-night terminator of the planet. Over here, you're seeing light emitted by the planet's day side. So at the end of my talk, I'll come back to this point, but just to say that even though these both allow you to measure composition, you're not measuring composition in exactly the same part of the atmosphere. So if you have a planet whose atmospheric composition varies, depending on which part of it you're looking at, these may give you slightly different answers. So the third technique that I'm going to tell you about today is a technique which actually doesn't require the planet to transit, although it's helpful if it does. So this is to measure variations in the brightness of the planet as a function of orbital phase. And so this is going to be really helpful for many of the transiting planets because they mostly have very short orbital periods. So we think that many of the transiting planets should be tidally locked. So they're going to have a permanent day side and a permanent night side. That may have significant consequences for the properties of their atmosphere. So going back to the chemistry, if you have a really hot day side and a really cold night side, you may have very different compositions in the two parts of the planet's atmosphere. If the planet that you're studying is a Earth-like planet around a low-mass star, it might be in the star's habitable zone and still be tidally locked. So you may also be interested in this question of circulation from the perspective of habitability as well. So what happens to tidally locked Earth-like planets in the habitable zone? Are they in fact habitable? Okay. So it's also helpful to keep some simple scaling relationships in mind. So whenever I sit down to write an observing proposal to measure any of these signals, the very first thing I do is I sit down and I do one of these two calculations. So this is just a back of the envelope, order of magnitude, how does the size of these signals scale as a function of various parameters? So the amount of absorption that you get during the transit from the planet's atmosphere is equal to the radius, the transit depth, which is rp squared over r star squared. You take the derivative of that, so 2rp over r star squared, and you multiply it by the thickness of the annulus that you think is doing the absorbing. So we can describe that as the scale height of the atmosphere. So that's a measure of how puffy or compact the atmosphere is. So that goes as the temperature of the atmosphere divided by the mean molecular weight times the surface gravity. So atmospheres that have a lot of hydrogen and helium have low mean molecular weights. Mu is small, and this term increases. So hydrogen and helium atmospheres will have very wide annuli that are absorbing, and they'll have strong absorption features during transit. Planets with high surface gravity, that makes the atmosphere more compact. That makes the signal smaller. So low density planets are more favorable for these kinds of observations. Increasing the temperature of the atmosphere, again, makes it puffier. So hotter planets are easier to observe using this technique. And another important term often, which is easy to overlook, is this rp over r star, and in particular the r star part. So everything that we measure with all of these techniques is measured relative to the star. So the size of the signal that we measure depends on the brightness of the star. If we can find the same planet transiting a smaller and cooler star, we can increase the size of the signal that we're trying to detect. So we can do Jupiters around sun-like stars easily enough with current telescopes, but if you want to do super-Earths, for example, those are very difficult if you have a super-Earth around a sun-like star. It gets much easier if you find that super-Earth transiting a low-mass star. So a similar relationship to predict the secondary eclipse depth. So you just have here the transit depth, rp over r star squared, and then this is just in the long wavelength limit, the ratio of two black bodies is just the ratio of the two temperatures. So this is a good approximation, sort of 5 microns and longer, depending on the temperatures of the things that you're looking at. So if you use these two relationships, you can get a rough idea of the order of magnitude of the signal that you're trying to detect. And so the sort of current trend in the field is that we've studied hot Jupiters. There's still lots of interesting questions to ask about hot Jupiter atmospheres. But we're currently trying to apply these same techniques to planets all the way down into the super-Earth regime. So the super-Earths are really kind of pushing at the limits of what we can do with present-day telescopes. Okay. And again, just if you replace these stars with M stars, I mentioned before this signal improves, but you'll notice there's also an R star term in here and a T-star term. So again, for both of these techniques, you gain when your star is small and cool. Okay, so what do we see when the planet passes in front of the star? So as I mentioned before, the wavelength-dependent change in the transit depth is going to vary depending on how puffy or compact your atmosphere is, which depends on the scale height of the atmosphere, which is this KT, where T is the planet temperature, G is the surface gravity, mu is the mean molecular weight. So up here is just a set of models calculated for a super-Earth, GJ1214, for anyone who wants to be specific, but this is probably a fairly representative set of models. So these models fall into two general categories. So this is transit depth as a function of wavelength. So absorption is up on this plot. When the atmosphere absorbs, the transit is deeper. So up here you have water absorption features, and then maybe a little bit of CO2 in this case, and perhaps a little bit of methane. So the top three models are all for hydrogen-dominated atmospheres. So you can see that even varying the metallicity by a factor of 50 has a relatively small impact on the shape of the features that you see. So all three of these models are hydrogen-rich, and all three of them have the same large variations in transit depth as a function of wavelength. So if this planet had this kind of atmosphere, we would have a relatively large signal that we would be able to detect. If, on the other hand, the super-Earth did not have a hydrogen-rich atmosphere, if it instead had a water-dominated or CO2-dominated atmosphere, those atmospheres have a much higher mean molecular weight. So this scale height gets smaller, and all of the amplitudes of these features decrease accordingly. So even though I said before this technique tells you the composition of the planet's atmosphere, you might imagine making lists of different molecules and measuring relative abundances, how much water does it have versus CO versus CO2. To 0th order, there's a single thing that you can get easily from these measurements, which is, do you see strong absorption features or weak absorption features? And that 0th order thing is mostly telling you about the hydrogen content of the atmosphere. So is this a hydrogen-rich atmosphere or a hydrogen-poor atmosphere? And so even with very relatively simple measurements, we can already perhaps answer the question that I posed earlier on, which is, if I have a low-density super-Earth, does it have a low density because it's a ball of rock with a hydrogen-helium envelope on top? Or does it have a low density because it's a ball of water with maybe a little bit of rock at the center and not much hydrogen? So I'm going to illustrate these techniques. I'm going to cheat a little bit, so I'm not going to show you observations for super-Earths. I'm going to show you an observation for a Neptune-sized planet. And I'm just doing that because all of these signals are larger for Neptunes. So we have nice high signal-to-noise measurements for this particular Neptune. So this Neptune is GJ436. It's about 20 times the mass of the Earth. It orbits a relatively small and cool star. So again, this makes it more favorable for these kinds of studies. And even though it orbits the star once every 2.5 days, because the star is small and cool, the temperature of this Neptune is only about 800 Kelvin. So by the standards of transiting planets, this is a relatively cool planet for us to study. And so this just shows you the system to scale. Okay, based on the mass and radius of this Neptune, you can estimate the range of hydrogen-helium mass fractions that are consistent with that mass and radius. And that range spans the hydrogen-helium mass fraction of Neptune. So on the face of it, with mass and radius alone, this appears to be a Neptune analog planet orbiting a small, cool star with a slightly warmer temperature. But we can check that. And the way that we can check that is first by observing it when it transits the star. So remember, what we're trying to measure here is the wavelength dependence of the transit depth. So here on the right is just an example of a set of transit light curves going across the visible. You might notice that the shape of the transit varies as a function of wavelength. That's due to limb darkening on the star. So the edges of the star are fainter than the center. That gives you that curvature during transit. So in order to measure the wavelength-dependent transit depth, we also have to have a good model for the limb darkening of the star as a function of wavelength. So all of the results that I show you are also going to be dependent on our understanding of the star's properties, and that's something to keep in mind. Our knowledge of the planet is only as good as our knowledge of the star in many cases. All right, so this planet was observed with the Hubble telescope in the near infrared, so 1.2 to 1.6 microns. So here I'm just showing you transit depth as a function of wavelength. So here in black are the data. In red is the model for what we would expect to see if this had a solar metallicity atmosphere. If I had shown you a Neptune-like atmospheric composition, it would look pretty similar to this. Neptune has a metallicity of about 70 to 100 times that of the sun. What you can see is that what we measure is basically constant as a function of wavelength. So we don't see the strong water absorption that we should have seen if this was a Neptune analog. So one explanation is that this is not a Neptune analog, that in fact this Neptune has a relatively hydrogen-poor, metal-rich atmosphere. So if you crank up the metallicity to 1900 times solar, 100 times more than that of Neptune, you would get something like the blue line. So that's just making the atmosphere more compact by taking the hydrogen out. There's a third explanation, which is that this is still a Neptune, but it has clouds in the upper part of its atmosphere. So if you add a high cloud deck, without changing the atmospheric composition at all, you can damp out this signature of these absorption features. So just to kind of give you a cartoon here, so clouds are going to block the absorption that you would otherwise see from this little blue annulus of atmosphere. So in this particular case, if this Neptune has clouds, they're probably either zinc sulfide or potassium chloride clouds, and that's just based on the pressure and temperature in the upper part of the atmosphere. Okay, so that would be if they were condensate clouds. I should also mention that you might have in some of these atmospheres photochemistry making kind of soots or long hydrocarbon chains more analogous to what we see on Titan. So I think one big question mark right now for exoplanet atmospheres is we see clouds in many of the planets, or we infer the presence of clouds, but we don't know exactly what the clouds are made of. And so it's difficult to predict in advance which clouds will have cloudy, or which planets will have cloudy or clear atmospheres. And this is a big problem for super-Earths because it takes a lot of Hubble time to measure the atmosphere of a single super-Earth. So if you can only do a couple with Hubble, you don't want to pick a couple, use all your telescope time, and then realize that you picked 3 cloudy planets and that you've learned nothing about the composition. All you've learned is that they're cloudy. And this is in fact what happened to the very first super-Earth observed by Hubble, studied by Laura Kreidberg. Okay. So secondary eclipse, moving briskly along. So these observations are now from the Spitzer Space Telescope. They're at somewhat longer wavelengths, 3 microns out to 24 microns. We want to look at longer wavelengths because this planet is only about 700, 800 Kelvin. So in order to have detectable thermal emission, we need to be kind of out in these wavelengths. So this is just the decrease in light as the planet moves behind the star, disappears, and reappears. So if we want to interpret these data in terms of planetary atmosphere models, we need to know a couple of things. First, we measure everything relative to the star. So we need a model for the stellar atmosphere. We need some models for the planet atmosphere. In this case, we can consider a very metal-rich model and a relatively metal-poor model, which is going to have different amounts of methane, CO2. We have our data here, the decrease in light when the planet goes behind the star. So out of eclipse, we measure the combined light from the star and the planet together. When the planet disappears behind the star, we see the light from the star alone. So what we measure is the difference between those two, which is just the light from the planet, divided by the out of eclipse brightness, which is the light of the two together. But we make an approximation that the star is much brighter than the planet. So to 0th order, this depth is just the ratio of the planet flux to the stellar flux. So all we need to do to compare our models to our data is take this planet model and divide it by this stellar model and plot it as a function of wavelength. So that's exactly what I did here. So this is just wavelength on the x-axis, planet-star flux ratio on the y-axis. So I've just ratioed the planet model to the stellar model. And then here in black are the secondary eclipses that I showed you before. So in this particular case, you can see that the planet is much better matched by the blue model, which is a very metal-rich model, and relatively poorly matched by the solar metallicity, kind of more Neptune-like model. So this is another line of evidence to say that this planet probably has a more metal-rich atmosphere, and so the threshold to match these data is about 300 times the metallicity of the sun. So it doesn't have to be all the way up to 1,000 times solar. It can be a bit less than that, but certainly, almost certainly more metal-rich than Neptune's atmosphere. Okay, so I wanted to also mention briefly the final technique, which is measuring the brightness of the planet as a function of orbital phase. So I kind of alluded before to why that might be interesting, that many of these planets have very short orbital periods, so we think that they probably are tidally locked. So if they're tidally locked, then you might have large temperature gradients between the day side and the night side. And you might also have chemical gradients that go with that. And so we can actually measure that directly by measuring changes in the brightness of the planet as a function of orbital phase. So when the planet goes in front of the star, you see the night side. As you watch going towards secondary eclipse, you see the day side rotate around into view. So that change in brightness, if the planet actually gets brighter at infrared light, tells you that the day side is hotter than the night side. So this is an observation of a hot Jupiter from Spitzer. So you can see again, it does increase in brightness as the day side comes around. So in this case, the planet has a day side which is about 1200 Kelvin and a night side which is about 1000 Kelvin. So for a hot Jupiter, that's telling you this particular planet probably has relatively strong winds going from the day side to the night side. Unfortunately, these observations haven't been done for Neptune-sized and smaller planets. These are even harder than the other two techniques that I mentioned before, but looking ahead to JWST, we'd like to do this for super-Earths, and we'd like to do this at multiple wavelengths as well. So this is an example of a recent observation of a hot Jupiter using Hubble from Kevin Stevenson. So here they're measuring the spectrum of the planet as a function of orbital phase in the infrared. So you can see not just the difference in brightness, so you don't have to assume the planet's a black body. You can actually see the change in its emission spectrum. So this is letting you actually check how the chemistry varies from the day side to the night side and how the pressure temperature profile varies. So it's giving you a lot more information than just that single wavelength of data I showed before. All right, so I've gone very quickly through the three sort of, I think, most popular techniques for studying exoplanet atmospheres. There are a multitude of questions that you can address with these techniques, but I tried to highlight a couple for you guys that I think represent some of the most kind of pressing or interesting questions in the field. So one question would be how the atmospheric compositions, and in particular the metallicity of these planets, varies as a function of their mass. That's going to tell us about how planets form and evolve, the relative importance of mass loss. We're interested in compositions specifically for super-Earths because we'd like to determine their bulk water content in order to figure out whether they formed in place or migrated from further out in the disk. We can only do that if we know whether or not they have hydrogen-rich atmospheres. Otherwise, mass and radius alone doesn't tell us the water content of the interior, at least for things with intermediate densities. And lastly, we talked a little bit very briefly about atmospheric circulation and how we can measure that using phase curves. And I think this is going to be an important question going forward as we start to look at small planets orbiting cool stars. So for a planet in the habitable zone of an M star, if the M star is cool enough, that planet is probably still going to be tidally locked. So a tidally locked Earth around an M star, is this the sort of thing that we would consider to be a potentially habitable planet? The answer to that is going to depend on atmospheric circulation. And lastly, that clouds are both interesting of their own right, but also make this picture much more complicated. So we would like to be able to pick cloud-free planets for observations in the future. So with that, I'll take questions. So like an oblateness due to a rapid rotation?
Yeah.
Could you repeat the question?
Yes, the question is, could you determine whether or not the planets were actually spherical or if they were oblate due, for instance, to rapid rotation? Yes, you might be able to see that in the shape of the transit light curve when the planet goes in front of the star. Ingress and egress are a little bit different for an oblate planet than they are for a circular planet. In practice, the signal is very small because if these planets are tidally locked, they're rotating much slower than Jupiter or Saturn. So no one has yet detected that effect for any of these planets. Yes, so we can kind of start to do that because I mentioned, yes, so the question is if we could study cooler super-Earths and not just the hotter ones, would they have a different mass radius kind of average density? We can start to do that if you compare super-Earths whose masses come from radial velocity measurements, which are typically very close in, versus super-Earths that have dynamically measured masses from transit timing variations, because those can be a bit further out. There's some suggestion that the transit timing variation super-Earths are lower in density than the super-Earths with masses from radial velocity, but I think the numbers are still a little too small to tell how distinct those two populations might be. They also might form differently, multiple planet systems versus single planet systems. So we need better data for sure. Yeah, so one thing that people have looked at with hot Jupiters is whether or not there's a temperature inversion in their atmosphere, meaning that temperature, you get up to a certain height in the atmosphere, normally temperature should decrease with increasing height. But if you have a gas that absorbs high up in the atmosphere, you can create a local hot layer. I think that there's probably the best evidence for temperature inversions right now comes from a recent paper on WASP-33 that had a spectrum from Hubble. So I think For most planets, it's ambiguous as to whether or not they have an inversion. So we probably need better spectroscopic data to get to the bottom of that question.